In this video, we're going to discuss heat engines and the efficiency of heat engines. So the basic idea of a heat engine is that you take heat in from a hot reservoir into the engine. You do some process inside of the engine that produces work, and you dispel waste heat into the cold reservoir. And the first law of thermodynamics says that energy must be conserved. So if I take in QH, remember heat is a type of energy transfer, so I gain energy QH into my engine, and my engine releases energy in the form of work and heat going into the cold reservoir. These two things together must add up to the amount of heat energy that we take into the engine. Now, the efficiency of the engine is basically the benefit that we get out of the engine in the form of work divided by how much energy we have to put into the engine in the form of heat. Now, we don't really count the heat that goes into the cold reservoir, as that's waste heat that is a necessary part of the cycle but can't be used to do any useful work. So our total cost benefit is the difference in the heat added minus the heat given to the cold reservoir, which it must be equal to the work, divided by the amount of heat that we put in. Now, we can relate this to simply the ratio of heats. So the efficiency is 1 minus QC over QH, which is just a restatement of the previous equation. But we can use entropy to see that this must be less than or equal to 1 minus T, the temperature of the cold reservoir, divided by the temperature of the hot reservoir. And to see why this is true, we need to invoke the idea of entropy and the second law of thermodynamics. In order to derive the relationship between the heat absorbed by an engine, the heat released by an engine, and the ratio of the temperatures of the two heat reservoirs, we need to begin by looking at a schematic and thinking about entropy. So, we know that the second law of thermodynamics says that the total entropy of the universe must increase or remain the same in any process. So, let's look at how entropy changes throughout the course of the engine. So, we begin by taking in some heat from the reservoir. As we do that, we actually drop the entropy of the reservoir by some amount, right? The reservoir, we haven't changed the number of particles, we haven't changed the volume of the reservoir, we've just taken some energy out. Less energy means less entropy, because there's less ways of rearranging a smaller amount of energy. So we have taken some amount of entropy out of the reservoir and put it into the engine. Then the engine does some work and it deposits its waste heat into a cold reservoir. In doing so, it adds entropy to the cold reservoir because the cold reservoir heats up as it gains this energy. And so we have entropy being transferred from the hot reservoir to the engine, from the engine to the cold reservoir. And now let's think about how these entropies relate to one another. So we know that for the engine, if we do a full cycle, that the total change in entropy must be 0 because the engine starts and ends in the same state. Same pressure, same temperature, same volume. And because entropy just depends on all of those variables, if the engine starts with all of those variables being in one state, and it ends with the variables being in the same state, same temperature, pressure, volume, it must have the same entropy at the end, which means that the engine's entropy doesn't actually change. Now, you might think, okay, well, it must take in the same amount of entropy as it gives off, and therefore it just doesn't have any entropy, or no change in entropy. But remember that unlike energy, entropy is not conserved. Entropy can always be created. So what we're really saying is that the amount of entropy that the engine takes in from the hot reservoir must be less than or equal to the amount that it gives to the cold reservoir. Because we can always make some extra entropy in the engine and give that to the cold reservoir. We can just never have less entropy than we started with, but we can always end with more. Okay, so how do we think about that? Well, the idea is that the total change in entropy of the system must then be just the changes of entropy of the reservoirs, because the engine doesn't gain or lose entropy over a full cycle. So for a full cycle, we have entropy lost by the hot reservoir, which I put a minus sign here to indicate that the hot reservoir is losing entropy. And then we have the entropy gained by the cold reservoir, and these two things together must be greater than or equal to 0. If we have the most efficient engine possible, this will be equal to 0. We will have created absolutely no extra entropy in the universe, and the entropy gained by the hot reservoir will be equal to the entropy lost by the cold reservoir. But if we solve this inequality, we find that the entropy lost by the hot reservoir must be less than or equal to that gained by the cold reservoir. Now, if we remember back to chapter 3, particularly on page 113 of Schroeder, there is a relationship between the change in entropy of a system and the ratio of its heat and temperature. Now, for quasi-static processes, that are processes that happen slowly enough that the state variables, things like pressure, temperature, are well defined throughout, this actually becomes an equality. That is, that the change in entropy is equal to the heat transferred divided by the temperature. And what we're going to do is we're going to basically assume that our engine always operates using quasi-static processes such that this is an equal sign. And that is a fairly good approximation for most engines. So we're okay with that. And using this equal sign here, we can now say that the change in entropy from the hot reservoir is just QH over TH. How much energy did we transfer divided by the temperature at which we transferred it. And likewise, the entropy of the cold reservoir that it gains is equal to QC over TC. And now we have a relationship here, just rearranging the variables, between the ratio of the heat transfer and the ratio of the temperatures for the two reservoirs, the hot reservoir and the cold reservoir. And this simply comes from looking at what the total change in entropy of the system needs to be and not letting that change in entropy ever be larger than 0 for the full cycle.
Now with our new relationship between QC, QH, TC, and TH, our ratio of temperatures and heats, we can replace our efficiency with 1 minus TC over TH and replace our inequality with our equal sign in the efficiency equation with an inequality, less than or equal to. This sets the maximum possible efficiency of a Carnot engine based on the ratio of temperatures of the hot and cold reservoir. And this efficiency limit comes simply from our second law of thermodynamics, that we cannot decrease the entropy of the universe by running our engine. Now, as a specific example of a heat engine, let's look at the most efficient possible heat engine, known as the Carnot engine or the Carnot cycle. So the Carnot cycle is a 4-step process Now let's look at a specific heat engine known as the Carnot engine or the Carnot cycle. The Carnot cycle involves 4 steps and is the most efficient possible cycle because it involves no change in entropy of the universe. Now, this is an idealization which can never be truly realized by any physical engine,
but we can approximate at least the Carnot cycle in physical engines. We'll begin at point 1 on the PV diagram, where the volume of the gas inside of the engine is at its maximum. From point 1 in the PV diagram, we expand the gas at constant temperature. This is given by figure C on the left-hand side of the screen. In this case, the gas is being compressed, and the excess heat from that compression is being dumped into the cold reservoir. So this is where we dump heat out of the engine into the cold reservoir. Obviously, as this gas is being compressed, it would like to heat up, right? Naturally, if a gas is compressed adiabatically, say, with no heat transfer, that gas will heat up. But in this case, we are allowing that excess heat to move into the cold reservoir. This brings us from point 1 to point 2 in our PV diagram. From point 2, we have further adiabatic compression. Adiabatic compression indicates that the no heat is transferred into or out of the gas. This is given by the picture D on the left. From the adiabatic compression, the gas is now at its highest possible pressure and lowest possible volume at any point in the cycle. And from here, we expand the gas isothermally. The gas naturally will try to cool down as it expands, and we replace the lost temperature due to the work that the gas does while expanding with heat from the hot reservoir. So this is where hot heat enters the cycle. And then we have adiabatic expansion, in which no heat enters and the gas is allowed to cool as it expands. This brings the temperature back down to Tc, so it is in equilibrium with the cold reservoir again. So essentially what we have is we have two processes that take place at different temperatures between 1 and 2 and 3 and 4, which are isothermal. So 1 to 2 takes place at a cold temperature, and 3 to 4 takes place at a hot temperature. And then we connect these two temperatures through adiabatic expansion and compression. Adiabats allow no heat transfer, and so the temperature of the gas changes as the gas does work, either has work done on it in compression or does positive work itself in expansion. Now, to prove that this cycle is the most efficient possible cycle for an engine, what we need to think about is the amount of entropy created. The most efficient cycle will be one in which no total entropy is created in the universe. That is, the change in entropy of not just the engine, but of the two heat reservoirs is 0 throughout the entire cycle. This makes the cycle completely reversible, which means that we could run this whole cycle backwards, and it would also create no total entropy in the universe. To see why the change in entropy is 0 for an ideal Carnot cycle, let's take a look at the two types of processes that happen in a Carnot cycle. The first type of process is some kind of an isothermal expansion or contraction. We'll look at isothermal expansion, but the exact same argument can apply to isothermal contraction. So here we have some heat reservoir at at temperature TH. It is giving heat to the gas inside of the engine as the piston expands. Now, what's happening here is that we are going to assume that the temperature of the gas is almost exactly the same as the temperature of the reservoir. Now, it has to be a little bit cooler, otherwise heat wouldn't flow from the reservoir to the gas, but it will be very, very close. Now, in this case, the heat is going to flow very slowly. Heat flow is dictated by a few things, but one of the major contributors is the temperature difference between the two objects where heat is being transferred. So if TH is the same, that is, the reservoir temperature is the same as the temperature inside of the gas of the engine, the heat flow is going to be very, very, very slow because the temperature difference is very small. But this allows us the almost zero entropy to be created. So if we say that the entropy lost by the reservoir is going to be delta SR, well, it's a negative value because our reservoir is losing entropy, and it's equal to QH over TH. And the entropy gained by the gas, on the other hand, is QH over TH as well. Now I put approximately here because the gas needs to be infinitesimally cooler than the reservoir in order for heat to actually flow from the reservoir to the gas, but we're going to say that it's effectively the same temperature. So in this case, since we have the exact same expression, the entropy gained by the gas is exactly equal to the entropy lost by the reservoir. So our total change in entropy during this process is delta SR plus delta SG, which is going to be 0 as long as they are at very, very, very close to the same temperature. So, of course, this is pretty unideal for a physical engine in that you would like your gas to be able to gain heat not infinitesimally slowly because it's just going to take a really long time to expand the gas while having it basically stay at the same temperature as the reservoir with the heat moving in very, very slowly. So real engines do not obey this kind of zero entropy change expansion, isothermal expansion, but for the Carnot cycle, it works. It has effectively zero entropy change for the universe. So for an adiabatic process, we have Q equals 0, which leads to du equals just W. But if W equals negative PdV, then du also equals negative PdV, right? And therefore, these two must both be 0. If Q is 0, then TdS is 0, as long as you're dealing with a quasi-static process. So we had TdS equals Q. This is true for any quasi-static process. Because we're adiabatic, Q equals 0, and therefore ds equals 0. Of course, we could say T equals 0, but that would be a kind of illogical solution to this problem. Just to say that it happens at absolute 0. None of our engines are actually working at absolute 0. That doesn't make any sense. So we must have 0 change in entropy. Together, we have found that adiabatic expansion, that is quasi-static, and isothermal expansion, which happens where the reservoir and the gas inside of the engine are both at approximately or almost exactly the same temperature, are both 0 change in total entropy processes, and therefore our Carnot engine, which uses both of these processes, is a 0 change in total entropy cycle. This means that it is the most efficient possible cycle for an engine that we can create. And any engine that does not follow the Carnot cycle can be no more efficient than a Carnot engine.
Now let's take a moment to consider refrigerators and the equivalent of efficiency for a refrigerator. So a refrigerator still must obey the first law of thermodynamics, which is just energy conservation. However, in the case of a refrigerator, energy is taken out of the cold reservoir, work is put into the engine, and then heat is transferred into the hot reservoir. So the net result is the cold reservoir gets colder and the hot reservoir gets hotter. Again, the total energy that goes into the engine is work plus QC, energy coming from the cold reservoir, and the total work or energy that leaves the engine is equal to QH. Since the total energy must be conserved, then QH must equal QC plus W. For a refrigerator, instead of the efficiency, we talk about the coefficient of performance, which is equal to the ratio of the amount of heat that you are able to take out of the cold reservoir, since that is the goal of a refrigerator, to remove heat from the cold reservoir, divided by the work that you have to put in. And this can be written as 1 over QH divided by QC minus 1. In the same way that we were able to derive a relationship between the heat transferred and the relative temperatures of the two reservoirs for the Carnot engine, we can derive a similar relationship for a refrigerator where we have switched the direction of the inequality. So now we have QH over QC is greater than or equal to TH over TC, indicating that the amount of entropy entering the hot reservoir must be at least as much as the entropy that was removed from the cold reservoir. Using this inequality, we can replace QH over QC with TH over TC in our coefficient of performance equation and replace the equals sign with a less than or equals to. Now let's look at the Carnot cycle for the Carnot cycle backwards so that the Carnot cycle is run as a refrigerator. So in this case, I have replaced the arrows that formerly made the Carnot cycle run in the clockwise direction with blue arrows that make the Carnot cycle run in the counterclockwise direction or backwards from its original direction. So to analyze this cycle, let's begin by looking at the isotherm that goes from point 2 to point 1. So this is associated with the isothermal expansion, because our volume is increasing, at the temperature of the cold reservoir. So at point 2, our engine is at the same temperature as the cold reservoir, and from there we expand the gas. As the gas in the piston or the gas in the cylinder expands, it cools down, and this heat that it loses, or the energy that it loses due to the positive work that it is doing in expanding the piston, is replaced by energy from the cold reservoir. So what we're in effect doing is using the expansion of the gas to cool the gas to a lower temperature than the cold reservoir's temperature, and therefore we are able to take heat out of the cold reservoir because we've made the engine colder than the cold reservoir. This is what happens from point 2 to 1 on the PV diagram. This is associated with diagram A on the left. Notice that heat is coming from the cold reservoir into our engine. The next thing that we do is that we compress the gas adiabatically. So we do not allow any heat to flow into the gas, but we compress the gas adiabatically from volume associated with point 1 to the volume associated with point 4. In this case, no heat flows into the engine, but the engine is the gas in the engine is heated based on this compression. So here we are doing work on the gas. An external object is doing positive work on the gas to compress it. This is where work enters the engine. Then what we do is we further compress the gas at this high temperature. And as the gas is compressed, it tends to heat up, and we dump that heat, that excess heat due to this isothermal compression, into the hot reservoir. So here we're making the hot reservoir even hotter than it was through this compression. And this takes more work done on the system in order to dump this compression, we're taking work, using that work to compress the gas, which heats up the gas, and then that excess heat from the gas gets dumped into the hot reservoir to keep the gas in the reservoir at the same temperature. This is associated with the diagram C on the left. Then what we do is we allow the gas to expand adiabatically. So in this process, no heat enters the gas. The gas is simply expanded without any heat transfer into the gas. This expansion causes the gas to cool down because the gas is doing positive work on the piston, removing energy from the system and cooling the gas inside of the engine.
And now we are back at our cool temperature associated with the temperature of the cold reservoir, and we're ready to start cycle A again, where we then isothermally expand the gas and kind of remove heat from the cold reservoir, further cooling the cold reservoir. So the total result of this process is that we have removed heat from the cold reservoir, then we have done work on the gas to then force heat to move into the hot reservoir. So we're making the hot reservoir hotter and the cold reservoir colder. That means that positive work must be done on the engine. This engine does not create positive work. It has positive work done on it.